Okay, so now let's move on to dummy variables, which many of you all have been asking actually. So far in our regression equation, we have included only numerical independent variables. So if it's like y equals beta naught plus beta 1 x1 plus beta 2 x2, and let me say that this y cap is sales, x1 is price, and x2 is advertising expenditure. Okay, all these variables are quantitative, right? That means they can be measured in numerical terms. So far we haven't included any categorical or qualitative items, that means which can't be measured in numerical values. So since we haven't included such categorical variables, does it mean that we can't? No, we can. So how can we do that? Categorical variables, by recoding them, we can change into dummy variables. I'm extremely sorry for my handwriting, as I'm like being sick for 2 days and now a bit fed up and really tired. That's why. Okay, don't care about it. I hope that it's like understandable at least. Okay, so we recode it as zeros or ones. Alright. So before moving on to anything, let me give like an example. So y equals beta naught plus beta 1. Instead of x, I'm going to write d because this is going to be a dummy variable. Okay. Okay. So over here, y is the wages and d is the gender. So I'm gonna recode it like this. D1i is equal to 1 if it's female, and 0 otherwise. That means if it's male, we will write 0. If it's female, we will write 1. Okay. Now you see gender has two categories basically. What are the two categories? Male and female. Though we had two categories, we only included one dummy variable. So what we said was number of dummy variables is actually number of categories minus 1. Why is that? Why didn't we include something like this? yi equals beta naught plus beta 1 d1 plus beta 2 d2 plus ei, where d1 is same as before. Okay, that means d1 represents 1 if female and 0 if it's male, and d2 represents 1 if male and 0 otherwise. Why didn't we do this? That's because, now let me do this and show you all. Y beta naught, or instead of writing like this, I can write it under this as well. Okay, I'm gonna form columns. Okay, and let's say I have 5 values. I'm asking from 1 person, second person, third person, fourth person, and 5 person. Altogether, I'm interviewing 5 persons. I'm asking whether you're a male or a female, and after that, I'm writing down their earnings as well. That is the wages. Okay, by default. So this is y1, y2, y3, y4, and y5. By default, this beta naught, which is a constant, we put 1. Okay. Under beta 1, if it's a female, we put 1, and if it's a male, we put 0. So let's say the second person I interviewed and the last person I interviewed was a female. So I put 1 for them and 0 for males. It will be the opposite over here, right? In B2, D2, these two were females, so I put 0, and the rest of them were males. Okay. Now, if I add these two together, that is D1 and D2, and form another column, D1i plus D2i, 0 plus 1 is 1. 1 plus 0 is 1. 1, 1, 1. Now you see, this column over here, beta naught, and this column over here are the same. Why is it the same? Because we have included two dummy variables for the two categories. Because of that, we fall into something called the dummy variable trap. What does a dummy variable trap mean? There is perfect multicollinearity. Remember when I taught you all the assumptions under regression? Okay. The second assumption was that the independent variables should be of non-zero variance. That means when you add an independent variable which gives the same information without any new information being added, then the variance between the two is 0. And that leads to something called multicollinearity, right? So here also we have the same thing. Beta naught already has this information of D1 plus D2. But since we are including both these categories as dummy variables, there is a repetition causing perfect multicollinearity. So perfect multicollinearity means no new information is added. Okay, so how do you overcome this? Now if you perform, as I told before, either you take the number of dummy variables. I'll write the solution over here. How to overcome? You take the number of dummy variables to be the number of categories minus 1. Or the other thing which you can do is you include all the categories as dummy variables, like what I've done here, D1 and D2. And exclude the intercept. You remove this beta naught. Alright. But moving further, we'll be mostly using this first method as only. Okay. Where we take the D to be categories minus 1. Let's see how we can interpret these dummy variables when it's included in the equation. So here we have y equals 10,000 plus 1,500 d. D is our dummy variable. So if it's a female, we consider it as 0, and if it's a male, we put as 1. And y indicates the salary. Okay. Now, in case this was a female, how do we find the earnings? How do we find the salary of this person if it's a female? Y is equal to 10,000 plus 1,500. Do we put 0 or 1? We have to put 0 for female. In that case, this is equal to 10,000. If it's a male, y is equal to 10,000 plus 1,500. Now we substitute 1 because we have to put 1 if it's a male. 1,500 into 1 plus 10,000 is 11,500. So when we are interpreting the coefficients, that is this beta naught and beta 1, how are we going to do that? So basically this 10,000 is the earnings of the female. So it's the value of the base category in simple terms. What is our base category? Base category is what we refer to as reference category, which means whatever the variable which we consider as 0. Here our 0 we have applied to females, so that becomes a reference category. So the intercept represents the value of the reference category. That is a value, that is the wages or salary received by females. And what does this 1500 show? 1500 shows us the increase in wages a male would receive in comparison to a female, right? A female will receive basically 10,000. If he is a male, if an individual is a male, he will get an additional amount of 1500. So basically this 1500 we can explain it as it's the estimated increase in predicted salary received by the males in comparison to the reference category. So what's our reference category? That's our females. So always the coefficient which we get over here, we have to compare it with the reference category. So here 1 is for males, right? So we say that's the increase in salary received by males in comparison to the females. As simple as that. Okay. Now in this first example, I have taken only one qualitative variable in our regression equation. One qualitative variable. Is it visible, guys? One qualitative variable, which has two categories. And we said that the coefficient 1500 is this. This is how you interpret 1500. And how do you interpret 10,000? That's the income received by females. Value received by the base category or reference category. Income or salary or whatever, okay. Received by females. Alright guys, so now let's take an example where we include one qualitative variable with more than two categories. So in our example, what we are going to take is we are going to find the salary of a teacher. And that teacher can be from either Colombo, Kandy, or Jaffna. Okay. So this is my equation, regression line. 50,000 plus 1,500 D1 minus 1,000 D2, and over here I'm going to consider Colombo as my base category. Colombo is going to be my base category. So if I'm in defining my variables, y is the salary, D1, I will put 1 if that person is from Kandy, 0 otherwise. And I will put 1 for D2 if that person is from Jaffna, and 0 otherwise. So if I don't put 1 for both the variables, that means that person is from Colombo. Understood, right? If I put 1 over here, that means that person is from Kandy. If I put 1 over here and 0 over here, that means that person is from Jaffna. If I put 0 for both, then that means that person is from Colombo. Now, when we are interpreting these values, what do we do? 50,000. As I said before, the intercept will be basically the salary received by the reference category. So 50,000 is the salary received by teachers in Colombo, teachers from Colombo. Intercept is always the value of the base category. This 50,000. Then what does this 1,500 indicate? That means if the person is from Kandy, then he will get 1,500 more than a person from Colombo, right? What did we say before? That's the increase in whatever y value in comparison to the reference category. So the estimated increase in salary of teachers in Kandy is in comparison to those from Colombo. Okay. Then we have another coefficient minus 1,000. What does this 1,000 mean? It's the estimated decrease salary of teachers in Jaffna, because D2 is for Jaffna. Always in comparison to those from Colombo. If you form the regression equation, it will be much clear to you. Now, if I do that, let's say we are finding the salary of teachers in Colombo. Okay, so how would be the equation? 50,000 plus 1,500. Is he from Kandy? No, so we put 0. Is he from Jaffna? No, we put 0. So the answer is 50,000. That is what we said over here. Then if that person is from Kandy, then 50,000 plus 1,500. Do we put 0 or 1? We put 1 because that person is from Kandy. Minus 1,000 into, is that person from Jaffna? No, so we put 0. So 50,000 plus 1,500 is 51,500. So this additional 1,500 is received by a person in Kandy in comparison to a person in Colombo, right? That is what I've explained over here. Then if I take to be the teacher is from Jaffna, so we take 50,000. Is he from Kandy? No, so we put 0. Is he from Jaffna? Yes, so we put 1. So 50,000 minus 1,000 is 49,000. So the difference between this 50,000 and 49,000, that is minus 1,000, is what I've explained over here. So a person from Jaffna receives 1,000 less than a person or a teacher from Colombo. Okay, so always when you are explaining or interpreting the dummy variable, you tell this it's an increase or a decrease of this factor in comparison to the reference category. Don't forget to add that. Alright. Now let's move on to another example. Here, all this while we have been considering only one qualitative variable. Now let's consider one qualitative and one quantitative. I'm going step by step so that you all don't get confused and it's very clear for you all, okay? So here my equation is going to be something like this. Y equals 200.09 plus 16.19x 1 plus 3.85d. So I've used x for quantitative variables and d for a qualitative variable. So here y represents the salary. Okay, let me take another example. Will you not salary, value of house. X is the size of the house size, and D1 I would say based on the garage is present or not. So if there is a garage, I will put 1. And I would put 0 if the garage is not present. Alright. Now here we have to be careful because we have included a quantitative variable as well. Now when we are interpreting the intercept, that is 200.09, if this dummy variable was not there, how would we have interpreted this 200.09? We would have said the value of the house, that is y, is 200.09 when the house size is 0. Yes, that is how we did before in simple linear regression, right? Before considering a categorical variable, that is how we explain. Okay, but now we have a dummy variable as well, and this dummy variable basically refers to the reference category when it's the intercept. So if we combine all this, we can say the predicted value of the house is 200.09 when this house size is 0 and what's our reference category? When a garage is not present. What have we done? When there is a quantitative and qualitative variable, we have to consider both of those into consideration when we are explaining the intercept. So this part shows the quantitative aspect. So we are saying the house size is 0. Here it shows the qualitative aspect where we are saying it is the reference category's value. So that is garage is not present is our reference category. Okay, I hope that is understandable. Now let's move on to the interpretation of the rest of the other variables. The next one is 16.19. So since there are two variables here, we have to keep one constant. What is going to be constant now? The dummy variable. So holding the presence or absence of a garage constant, okay, when this is constant, the predicted value of the house is expected to increase by 16.19 when the house size increases by 1. Correct, right? Okay. Remember about the fact this is a multiple linear regression. So when we are interpreting one independent variable, we have to keep the other one constant. So that's what I have said over here. The presence or absence of a garage is constant. Okay. Then we have to explain this 16.19. What does it mean? When we increase the size of the house, that is x1 by 1 unit, what is gonna be the change in our dependent variable? That is the value of the house is gonna increase by 16.19. Now you all can pause the video and try out explaining or interpreting the other one, 3.85. What does that basically mean? We have to hold the size of the house constant now. Holding the house size constant, when we increase the size of the, sorry, when we, this is not increase, I'm sorry. When, even I got a bit disturbed. Okay. So we say when the house of the size is constant, the predicted value of a house with a garage, because with a garage only we have assigned 1, is 3.85 more in comparison to a house without a garage. These are very small minute things which you have to consider when formulating the entire interpretation for that variable. See, since because it's a multiple regression, at the beginning itself we say we are holding the other variable constant. Other variable is this 16.19. Okay. We are ignoring this at the moment. And we are going to consider this. So the other variable 16.19 is constant. Now we are dealing with the quantitative or qualitative variable. Qualitative, that means it's a dummy variable. So we say predicted value of a house with a garage, for what we have put 1 with a garage, is 3.85 more in comparison to the reference category, that is without a garage. Alright. Now let's move on to the final example where we'll be including one quantitative and one qualitative with more than 2 categories. Okay, so my equation is going to be like this: y equals 200.19 plus 16.19 x1 plus 2.36 d2 plus 4.52 d3. I've used the same example as before, guys. So this 200.19 you know, 16.19 also you know. The new variables which I've included over here is this d2 and this d3. So I'm going to refer to d2 as 1 if there is 1 car garage and 0 otherwise, and d3 if there is 2 car garage. So what is my base category over here? If these two values are 0, then basically It shows that there is no car garage, zero car garage. That's my base category. Base, or we can refer to as reference. This is what we are referring to. That's why it's called the reference. Okay, I hope the question is clear. 16.19 X is the house size. In the previous example, we had only included two categories, that whether the garage is present or not. Here we are including three categories, that is garage, there is one car garage, there is two car garage, or there is no car garage in the house. So I'm going to put 1 for D2 if there is one car garage. I'm going to put 1 for D3 if there are two car garages. And if both are 0, then that means there are no car garages at all. Now, how do we interpret this 2.36? That's the question. Okay, so is this multiple linear regression? Yes, so we have to keep the other variables constant. So there are only two variables, that's the house size and the presence or absence of a car garage. So since we are talking about the car garage over here, we have to keep this constant. So holding house size constant, the predicted value of the house, we are talking about D2, right? Predicted value of a house with how many car garage? D2 refers to 1. So predicted value of a house with one car garage is estimated to increase by 2.36 in comparison, always in comparison to the reference category, that is a house without a garage, in comparison to a house without a garage. As simple as that. Now you can try 4.52. How do you interpret that? Again, there are two variables, so we have to hold the other one constant, that is the house size. D3, we are talking about two car garages, so we say predicted value of a house with two car garages is estimated to increase by 4.52 in comparison to always a reference category, again to a house without a garage. So what I want you all to do is, basically guys, we have discussed 4 examples. The first one with only one qualitative variable and two categories. The second one qualitative and more than two categories. Then in the third example, we added a quantitative variable with two categories, and in the fourth one we have considered one quantitative and one qualitative which has more than two categories. So if I go through this, and if you all are very familiar with these 4 examples, then you all can write the interpretation for anything, I would say. So consider the minute things. When there is multiple linear, then you have to keep another variable or the other variables constant. When it's a dummy variable, you have to always compare it with the reference category. When you're explaining a quantitative variable, you can say when there is an increase by x1 by this amount, then the y will increase or decrease by this amount. Okay, so keep those chuti small points in your head, and when you're writing the answer or when you're interpreting, you can put all them together and write. Now let's consider another part or another aspect of this. So here, if we had taken that example, I think that was the third example. where we had this house with a garage and house without a garage. So I said this is the equation y equals 200.16 sorry 200.09 plus 16.19 x1 plus 3.85d. Okay, so if the house had a garage, is a garage, then y equals 200.09 plus 16.19 x plus 3.85, we substitute 1. Okay, so if I draw the graph, this is that equation if the house has a garage. If the house doesn't have a garage, no garage, then y equals 200.09 plus 16.19 x plus 3.85 into, what do I put here? I put 0. Now will this line come above the house with a garage or below? It's gonna come below. Why? Because over here, if you see this 3.85 into 0, the entire thing becomes 0. So this is the equation which is remaining. But here this 3.85 into 1 is 3.85. So you have to add over here. So the final equation would be 238 point something something plus 0. So that is definitely greater. So this house with a garage will come up, red color will come up and blue color will go down. So by adding a dummy variable in an equation, what has happened? Your intercept has changed, right? Intercept has increased from here to here. So intercept changes. But does your slope change? No, the slope remains the same. Slope no change. It remains the same. Now when we move on to the concept called interaction term, you will see that this will not be the case because over there your slope is going to change with the intercept because of the interaction term which is being added. But for now, just remember, if there is no interaction term, only your intercept will change, the slope will remain the same. Now if I say that I'm gonna switch my dummy variable, the categories, okay, now over here I considered 1 if the garage is present, right, and 0 if the garage is not present. But I want to switch these two variables. I'll write that separately and show. Okay, so y is equal to 200.09 plus 16.19 x plus 3.85, and d is 1 when there is a garage, so I'm going to put g over here, so it is easily identifiable now. If there is a garage, you're going to put 1 for g. Now we have only two variables or two categories over here. Either you have a garage or you don't have a garage. So g plus ng is equal to 1. Now can I say g is equal to 1 minus ng? Yes, I can say that. So now I can switch the variables very easily. Now if I want to make this g to ng, what do? I can write it as, instead of ng, I can write it as 1 minus ng. Okay, I haven't changed anything. Okay, g, another way to write g is 1 minus ng, right? G is 1 minus ng. Okay, I'm writing the same thing, no difference. I'm not going to change anything. Let me write the rest also like that. 3.85 plus 16.19x plus 200.09 equals y. Now, if I go ahead and simplify 3.85 into 1 is 3.85 minus 3.85 ng 16.19x. Let me keep that in red itself now so that it's very clear for you all. Plus 200.09y. Now we can add these two. So when I add that, what will I get? What is 200.09 plus 3.85? 203.94. So my intercept is now changing. (16.19x) minus 3.85 ng. Now if you all notice, my intercept has changed. How? Because we have added this 200.09 and 3.85. So as a result, intercept changes. What about my coefficient of the dummy variable? Has it changed? Here also it's 3.85, here also it's 3.85. But however, if you have clearly noticed, here it's a plus, here it's a minus. So what can you conclude based on this? When you switch the variables, not the variables actually, when you switch the categories of a dummy variable, your intercept will change. Then if we consider your slope, the sign changes. That is, plus becomes minus or minus becomes plus. However, the value doesn't change. If you had done the regression in a Excel, you would have also noticed that even if you switch the categories of a dummy variable, your other stuff like R square, adjusted R square, SE, that is the standard error. I'll write it as standard error if not, again, confusion, standard error of estimate, p-value, f-stat, nothing would change. Because why? There is no new information added. You're simply changing or interchanging the categories. Previously you said that's the equation for with a garage. Now you're saying without a garage. So since there is no information added, all these values won't change. It will be only a change in your intercept, and even the slope doesn't change, but only the sign changes. Okay, so keep this in mind as well. Now we will move on to the topic of interaction terms. Interaction terms is also basically nothing, guys. It's simple. If you think that your independent variables are related to each other, okay, If you all remember, I took this example where we talked about wages being dependent on education, the number of education years of education, and gender, right? So over here, education is definitely going to affect the salary you're going to get. Gender, being a male or female, also affects the wages you're going to get. Being a gender, sorry, being a female, do you think that's going to limit your number of years of education? We can say that, right? So if you are a, that is prevailing in the society, usually when you are a male, then you get to study further. Now it's changing since with all these advancements and all these positive attitudes towards gender discrimination, trying to eradicate that, obviously that is changing, but still you can see that it's prevalent in some areas of the world where females are not able to continue their higher education. So definitely there is a relationship between gender and education. So if you don't consider the relationship between these two in your regression equation, then it's gonna be a biased or a misleading equation. The wages are not gonna be predicted properly. So you introduce an interaction term. How do you introduce an interaction term? You say beta 3, where you consider both education and gender. So basically the product of these two is the interaction term. So usually if you have a regression equation, so this was a previous regression equation, right? Wages equals education and gender. So what you do is you check individually if this is individually significant or individually significantly impacting to the wages by doing a t-test for slope. Then you do a t-test for this as well. Alright. Then what you do is you add this interaction term. So what is this interaction term basically? Two independent variables multiplied together, right? X1 into x2. After that, you will form this big equation considering the interaction term. And after that, again you check what has happened to the t-test, education by doing a t-test. Again t-test for this and a t-test for this as well. Then you can see by adding an interaction term whether it has significantly impacted your wages and whether these education and gender related factors are also showing a relationship or not. That's basically the reason for that. Okay. Another important thing which you have to remember is when you are introducing an interaction term, so here education into gender, then your final regression equation or model shouldn't omit these two factors. Individually these two should be present. In education should be there individually, gender should be there. Then we have the interaction term education into gender. You can't just simply write wages equals beta naught plus beta 3 where we consider only education and gender. No, this is wrong. Let's do that same example as before where we consider the garage and without a garage, that example. Okay, so I'm going to say y is equal to, I'm going to change the values a bit. Okay, 212.95 plus 8.36 x1 minus 11.84 d2. I'm writing d over here to show that's a dummy variable. X, d and all are independent variables. To differentiate, I'm just writing d. Okay, and plus 9.52 x1 into d2. So here y represents the house size. Sorry, y is the value of the house. X1 represents the house size. D2 is 1 if there is a garage. Then we have X1 into D2, which is the interaction term, house size into garage. Before you go and interpret these values, you have to, it's basically, I would say it's good if you all can identify the separate equation for both the, like with the garage and without a garage. Okay, so let's do that first. So if it's without a garage, that means we are considering D2 to be 0, right? So y equals 212.95 plus 8.36 x1 minus 11.84 into something plus 9.52 x1 into something. What is that something? It's 0 because we are considering a house without a garage. So these two values will be basically 0. So you end up with the equation 212.95 plus 8.36 x1. Now if we consider a house with a garage, then wherever there is D2 you have to plug in 1. 8.36 x1 minus 11.84 into something plus 9.52 x1 into something. What is that something? It's 1. Okay, so if you solve this, 212.95 plus 8.36 x1 minus 11.84 plus 9.52 x1. Now let me highlight these and show. These two are the light terms which you can add together. Then the other two ones are these two which you can add together. So if I write that down, 212.95 minus 11.84 will give you 201.11 plus intercept has changed now. Previously it was something, now it's something else. But about the slope, 8.36 plus 9.52, 17.88 x1. So if you all see, before with without a garage and with a garage, both the intercept has changed and the slope has also changed. Slope changes, intercept too changes. So your graph would look like something like this. 201, that means with the garage, will come below like this. And without a garage will be like this. Right? You all agree? if you can see, because the intercept, look at the intercept, guys. 212.95, and this is 201.11, and you all can see the slope has also changed. Here for the red one, the slope was 8.36, and if it was without a garage, the slope is, I'm sorry, this is 8.36, and if it's with the garage, you will have 17.88. I hope it's clear for you all now. So when you add an interaction term, remember that you have to multiply those two independent variables, but you shouldn't omit their individual ones as well. You have to include them. So see, I have x1 separately, d2 separately, then both of these together as well. Let's look into the interpretation of the regression coefficients when there is an interaction term. You can see we have an interaction term of 9.52 x1d2. Okay, guys, please make sure that you are very thorough in this area, that is interpreting the variables, because I remember Miss saying that she'll be allocating around 20 marks just for interpretation. Okay, so by the end of this, you all have to become experts. I hope so. If not, no point now. And make sure that when you all are coming for the exam as well, you have clearly understood this part. If you all haven't, asked from someone and get it clear, because this is an area where you can easily score marks. Okay, so let's just go through quickly. So 212.95 is our intercept. So what did I say? When it's an intercept, that means all your quantitative variables are equal to 0, and you are when it's a dummy variable, you are referring to the reference category. Okay, so 212.95 is basically the predicted value of your house. House is 212.595 when house size is 0 and the house doesn't have a garage. Next is 8.36 x1. So is this a multiple linear regression? Yes. So if you're talking about the house size, we have to keep the other one constant. So we can say when, or we can start off saying holding absence or presence of a garage constant, same as before. Okay, when house size increases by 1, then the value of the house, the predicted value of the house, or you can say the average predicted value of the house, is estimated to increase by 8.36. Then we have minus 11.84. Again, multiple linear regression. We are focusing on the dummy variable now. We have to keep the other one constant. So holding house size constant, the predicted value of the house with the garage is 11.84 rupees less in comparison to a house with a garage, without a garage, to a house without. our base category or reference category. Then we have our interaction term, which is the new thing we are learning, 9.52 x1 into d2. So what can you say about that? Are you holding any variable constant? No, because both are being considered over here. What can you say about the house size? When it's increasing by 1. And what can you say about the dummy variable when there is a garage in comparison to one without a garage? These are the ones which we considered when we are explaining it separately. Now we have to put everything together. So we can say the predicted value of a house I am extremely sorry for my handwriting, guys. Didn't hope to be like this, but it's coming that way. Predicted value of a house increases by 9.52 rupees, 9.52 more for each 1 unit. Over here I have made a mistake, right? House size increases by rupees 1. This is not rupees either, it should be square feet or whatever, not rupees over there. Okay, so 9 predicted value of a house increases by 9.52 more for an additional, for an increase in house size by 1 for a house with a garage. So here itself we can include that, right? Predicted value of a house with a garage increases by 9.52 more for an increase in house size by 1 in comparison to a house without a garage. So since all of this is multiple linear regression, we have included an interaction term. So we are not keeping anything constant over here. So we don't include that part, holding constant something something blah blah blah. No, we don't include. Now we have two variables, the house size and the absence or presence of a garage. So one is quantitative, one is qualitative. So for the quantitative, you say when this increases by this much, by 1 unit, what will happen to y? And for the dummy variable, you say when this garage is present in comparison to the reference category, this is so both together it will give you 9.52. All right, so basically when the house size increases by 1 and when you have a garage, your value of the house increases by 9.52 in comparison to a one without a garage. As simple as that. So make sure you practice this very well and you are very thorough in this area. Now let's move on to quadratic regression model. Have been doing this throughout and I'm like gone mad a bit. Excuse me for that, guys. Okay. Now quadratic regression model. Okay, so here there is not much big scene. It is also easy. If you take it easy, it's actually easy. So if any of your independent variables have a degree, then it's called a quadratic regression, right? So your population regression model would be like this. Population model is yi equals beta naught plus beta 1 x1 I plus beta 2 x1. This, for this same variable I'm going to put a square term, x1 square. That is one thing I've noted as well. So when you're introducing based on the slides also, when they are introducing an x square, the square term, what Miss has taken is she had taken this variable, squared it and included here as well. That's not the case every time, but based on what we have learned so far, this is how it has been. Okay. So if I am writing the sample model, so we simply put the caps beta naught, beta 1 cap, x1i plus beta 2, x1, this thing. So if you can see, this x1 is a linear term. As a result, this whole thing will have a linear effect. This x square is a square term, a quadratic term. As a result, this will have a quantitative effect on y. Now, when we are interpreting the slope in the previous ones, simple linear regression, y equals beta naught plus beta 1 x, we said that when x increases by 1 unit, beta 1 will the y will increase by beta 1. That's how it was, right? But over here it's a bit different, because when we find the rate of change, that is, if you find the differentiation derivative of this equation over here, then it's actually you apply partial differentiation. So in terms of x, so beta naught is a constant, so that will be 0. This term, beta 1 x1, beta 1, then beta 2 x square, you bring the square in front, right? Remember guys, calculus, differentiation, we bring the 2 in front, b2 x2, sorry, it's x1, no? x1. Okay, so this is the rate of change. I'll remove this 0 as well so that it's not complicated. So in simple linear regression and basically when there is a linear regression, when x increases by this amount, it will increase, the y will increase by the slope coefficient itself. But over here in quadratic regression, it will not increase by this beta 2. It will increase by beta 1 plus 2 times of beta 2 into the x. Okay. If you all know the theory, that is very well enough. And in case if you are given the r square for this, let's say r square is equal to 0.7. So for a quadratic relationship equation or model, r square is 0.7. You explain it saying 70% of the variation in y is explained by the quadratic relationship between x and y.